Good morning, students. We already discussed the topic of developable surface, and today we'll discuss another definition of developable surface in terms of Gaussian curvature. Gaussian curvature we already discussed, which is the ratio of ln minus m square and eg minus f square. So in terms of Gaussian curvature, a developable surface can be defined as the surface for which the Gaussian curvature is 0. So Gaussian curvature is ln minus m square divided by eg minus f square. So if this term is 0, from here we get ln minus m square, that will be 0. So we will do the theorem based on this definition. So the theorem is necessary and sufficient condition for a surface to be developable is that its Gaussian curvature should be 0. Now what is developable surface? Developable surface is the surface which is generated by the tangents to the edge of regression. If the curve which is edge of regression is denoted by the equation given by vector r is equal to vector r, which is the function of s, then the equation of developable surface is given by vector r is equal to the vector r plus v into vector t. Here this capital R, this is the position vector of current point on the generator. This v is the parameter, t is the tangent vector to the curve. Now we will use the suffixes 1 and 2 for the partial differentiations with respect to s and v respectively. Now in the necessary condition we prove that the Gaussian curvature is 0. It means we are to prove that ln minus m square, that is 0, where L, m, n are second fundamental magnitudes. To find the second fundamental magnitudes, we require the second order partial derivatives of this vector. So let us find the partial derivatives of second order for this vector. So firstly, differentiating this vector partially with respect to s. The derivative of this vector r with respect to s, that will be dr by ds, which is the unit tangent vector t. Here v is constant. The derivative of vector t, that is given by dt by ds, which is by Serret-Frenet formula, that is given by kappa into n. Now differentiating the vector r partially with respect to the parameter v, that we have denoted by the vector r2. So differentiating with respect to v from here, because this is the function of s, so its partial derivative with respect to v, that will be 0. The derivative of v, that will be 1. So the vector r2, that is given by the vector t. Now let us find the cross product of r1 and r2. Now r1 cross r2. Now r1 cross r2 means the cross product of t plus kappa n v cross t. Now t cross t will be 0. So from here we get r1 cross r2 is equal to minus k into v into the binormal vector b. Now again differentiating this vector partially with respect to s. Derivative of vector t with respect to s, that is given by Serret-Frenet formula, which is kappa into n. And here, because we are differentiating with respect to s partially, so v is constant, using the product rule between kappa and n. So by using product rule, kappa will remain as it is, and derivative of vector n, that is by Serret-Frenet formula, which is given by tau into b minus kappa into t, plus v and n as it is, the derivative of kappa, that is kappa dash. Now let us find r12. R12 means its partial derivative with respect to v. So its derivative will be 0, and here the partial derivative with respect to v, that will be kappa into n. Now R22 means second order partial derivative of vector r with respect to v. So its partial derivative with respect to v, that is 0. So we have obtained all the second order partial derivatives of the vector capital R. Now let us find the normal unit vector. Now by definition, the normal unit vector, that is given by r1 cross r2 divided by h. Value of r1 cross r2, that is minus kappa into v into vector b, and divided by h. Now let us find the second fundamental magnitudes L, M and N. Now by definition, as we discussed in the chapter 4, L is given by the dot product of the normal unit vector n with the vector r11. Now n dot r11 is minus v square kappa square tau divided by h. M is given by vector n dot r12. Now because substituting the value of vector r12 and n, substituting the values, now because the vector b and normal vector n, they are perpendicular to each other, so b dot n will be 0, so r12 dot n, that will be 0. Now third fundamental magnitude n, which is normal unit vector dot r22, that is 0 because the vector r22 is 0 vector. We have obtained the values of L, M and N, substituting the values in the formula for Gaussian curvature. The Gaussian curvature is given by ln minus m square divided by Eg minus f square. Now if we substitute the values of L, M and N here, we get the value 0 because M and N both are 0. So this proves that if a surface is developable surface, then its Gaussian curvature is 0, and this proves the necessary condition. Now let us prove the sufficient condition. In the sufficient condition, we are given that the Gaussian curvature for the given surface, the equation of the surface, we have taken vector r is equal to vector r as the function of parameters u and v. The Gaussian curvature for this surface, that is 0. It means ln minus m square is 0, and we are to prove that the surface is developable. And we already discussed a surface is developable surface if it is the envelope of single parameter family of planes. So we will prove this condition to prove that the surface is developable. Now because ln minus m square is 0, let us find the values of this expression. Now by definition, L, M and N, as we discussed in chapter 4, L is given by minus n1 dot r1, M is given by minus n1 dot r2 or minus n2 dot r1, and N is given by minus n2 dot r2. Here this n is not a vector, this is the second fundamental magnitude n. Substituting the values of L, M and N here and using the Lagrange's identity of vectors. What is Lagrange's identity in vectors? If we have the four vectors, vector A, vector B, vector C and vector D, then the dot product of vector A cross B with vector C cross T, that is given by the determinant in which the first row has the vectors A dot C and B dot C. In the second row, we have the vectors A dot D and B dot D. This identity is called Lagrange's identity. So using this identity here, this expression can be written in this form. Here, the vector A is vector r1, vector B is vector r2, vector C is vector n1 and vector D is vector n2. So by using this identity, the value of ln minus m square becomes r1 cross r2 dot n1 cross n2. Now what is r1 cross r2? That is the product of h and the normal unit vector n. So this will become h into vector n. So this expression will become h into the scalar triple product of vector n, vector n1 and vector n2. Now because we are given Gaussian curvature is 0, it means this expression will be 0 because h is not equal to 0. Now the scalar triple product of vector n, vector n1 and vector n2, that is 0. It means n dot n1 cross n2, this is 0. Now the dot product of two vectors is 0. Either the first vector will be 0 or second vector will be 0 or both vectors will be perpendicular to each other. But this vector is not equal to 0. Now this vector cannot be perpendicular to this vector because the vector n, that is always perpendicular to n1 as well as n2. So that will be parallel to their cross product. So this vector cannot be perpendicular to this vector. So we have only one possibility, that this cross product, that should be 0. It means n1 cross n2 is 0. Now the cross product of two vectors is 0. So either first vector will be 0 or second vector will be 0 or both vectors will be parallel to each other. So we have three possibilities. Either vector n2 is 0 or vector n1 is 0 or n1 is parallel to n2. So we discuss the three cases one by one. Now let us take the first case when the vector n2 is 0. Now because we have to show that the surface is developable surface, it means we have to prove that it is the envelope of single parameter family of planes. So let us write the equation of tangent plane at any point of this surface. This equation we have already discussed in the previous chapters. Equation of tangent plane at any point of given surface is given by vector r minus r dot n is equal to 0. We have to show that this equation contains only one parameter u. It means we have to show that this is independent of parameter v. So if we differentiate this with respect to v, that derivative should be 0. So differentiating partially with respect to v, this expression. So from here the derivative of this term, that will be 0. Derivative of vector r with respect to v, that is vector r2 dot n plus r minus r as it is. The derivative of vector n with respect to v, that is the vector n2. Now because r2 is a tangential vector, this is the normal unit vector, so these two vectors are perpendicular to each other, so their dot product will be 0. Also the vector n2 we have taken 0 in this case. So we have obtained the partial derivative of this dot product with respect to v, that is 0. So we can say that this expression is independent of v. Thus we have proved that the equation of tangent plane contains only one parameter u. And by definition we can say that if a surface is envelope of single parameter family of planes, then it is developable surface. In the same way, if we take n1 is equal to 0, we can prove the surface is developable. Now let us discuss the third case when the vector n1 and vector n2 are parallel vectors. If two vectors are parallel, it means they are some multiple of each other. So we can take vector n1 is equal to mu into n2, where mu is some scalar. Now if we transform these parameters u and v into some new parameters by using some transformation, we will show that even in that case the equation of tangent plane contains only one parameter, or we can show that the normal is dependent only on one parameter. So let us apply some transformation of the variables. So let us take u is equal to u dash plus v dash and v is equal to u dash minus mu into v dash. Now let us find the partial derivatives of normal unit vector with respect to these new parameters. So curl n by curl u dash, this is given by curl n by curl u into curl u by curl u dash plus curl n by curl v into curl v by curl u dash. Now this is n1 and this is vector n2. So we have obtained the partial derivative of the normal unit vector n with respect to u dash is equal to vector n1 plus vector n2. Now, the partial derivative of the normal unit vector n with respect to the parameter v dash, this is given by the partial derivative of n with respect to u into the partial derivative of u with respect to v dash plus partial derivative of n with respect to v into partial derivative of v with respect to v dash. Now, this is given, this is n1 and this is 1 and this is n2, this is minus mu. So, we have obtained the value. The partial derivative of n with respect to v dash is n1 minus mu n2. But in this case we have taken n1 is equal to mu into n2. So, this will become 0. Thus, we have shown that the partial derivative of vector n with respect to this parameter v dash, that is vanishing. It means the surface normal is dependent only on one parameter. Thus, in this case also we can say that the surface is developable. So, this completes the necessary and sufficient condition for a given surface to be developable.